In section 4.3, we're going to take the next step in curve sketching and learn about the mean value theorem and monotonicity. When we're talking about the mean value theorem, we're actually talking about something that makes great fundamental sense. For instance, if I knew that I had reached a maximum speed on the interstate on the way to work of 80 miles per hour, so I traveled between 0 miles per hour and 80 miles per hour, the mean value theorem basically guarantees that at some point, whatever my average speed was, let's say 72, I had to travel through that speed. So when I travel from 0 miles per hour to 80 miles per hour, at some point in my travels I had to hit the average speed of how I was traveling. And what the mean value theorem then does is it talks about at what time did that happen. But of course we won't talk about this in terms of speed, but we're going to talk about this in terms of tangent lines, slopes of tangent lines, and points on a graph at which this average speed would occur. To talk about the mean value theorem, which we often abbreviate MVT, we need to recall that the derivative determines whether a function is increasing or decreasing, because the derivative talks about the slopes of the tangent lines. So if the slope of the tangent line is defined by f prime of x, which we know that it is, the derivative is a rate of change, then the function is increasing if the first derivative is greater than 0 or positive. The function is decreasing if the first derivative is less than 0 or negative. So again, this gives us an idea about what the function will look like. Talking about the very definition of the mean value theorem, it's not really clear, but as soon as we start looking at some graphs, we'll be able to see exactly what it's talking about. When we talk about the mean value theorem, the function always assumes continuity, of course. That means we can't have any jump discontinuities or hollow points in the graph. And we say it's continuous on a closed interval AB, and of course closed interval has bracketed points. It's differentiable on the open interval AB because we know we can't take a derivative at one of those single endpoints because I wouldn't have a nice slope of my tangent line and an endpoint. Then what the mean value theorem says that there exists at least one value of C in the interval AB. So there's some value of C between A and B. So in our example, there was some value of C or some value of time between 0 and 80 miles per hour that was my average, such that f prime of C will be the rate of change evaluated at some constant C, or the slope of the tangent line, is equal to f of B minus f of A over B minus A. Now this formula, f of b minus f of a over b minus a, should look pretty familiar. We worked at this toward the beginning of the semester. This is the slope of the secant line. So what this is saying is there's some point C where the slope of the tangent line and the slope of the secant line are the same. Because the slope of the tangent line and the slope of the secant line are the same, then we can say that they're parallel. So another way to talk about the mean value theorem is we can say that there exists at least one tangent line that is parallel to the secant line in the interval AB. The secant line is produced by plugging in these endpoints A and B. So if we were to look at this graphically, this could make a lot more sense. So what we can see from our graph here is, first of all, I have these 2 points A and B, and I've produced a secant line that goes through the points A and B. So what the mean value theorem says, there exists at least one tangent line that is parallel to this secant line. So here's a copy of that secant line, and let's see if we can move it up till we find a point that it's tangent. And we can see that it's tangent right there. Well, actually we could have moved it down a little bit, but we can see that it's tangent right here at this particular point. Okay, so what the mean value theorem does is it guarantees the existence of this point C at which this will occur. So this was the secant line, and the mean value theorem guarantees that between this interval A and B, there guarantees this point C that if I plug in this C, I'll get this tangent line that has the same slope. So here's my tangent line, and both of these have the same slope. They're parallel lines. Now, moving the secant line until it's parallel is kind of a good way to find this tangent line, but we also have to be able to use not just a picture to do this, but actually use some math to do this. And because we're talking about tangent lines and secant lines, you know that somehow it will involve derivatives. Now Rolle's theorem, which is a special case of the mean value theorem, is something that we talked about before. Now with Rolle's theorem, what ends up happening is f of a and f of b are the same. So instead of being a little bit higher and b a little bit lower, Rolle's theorem would have a line like this, and then of course my parallel line would be somewhere up here for Rolle's theorem. But the Rolle's theorem is a special case of the mean value theorem. Now let's go ahead and look to see how we'll solve one of these types of problems mathematically. So let's look at an example where we're asked to apply the mean value theorem. So for this example, we're going to find this point C on an interval satisfying the conditions for the mean value theorem. So the point C that we're going to find has to lie somewhere between the point 4 and the point 9. So these are values of x, 4, and 9, and I'm looking for a value of C between 4 and 9 that will satisfy the conditions of the mean value theorem. Well, when we're using the mean value theorem, the first thing that we need to remember is kind of its definition. So let's go ahead and first of all look at the derivative, because the derivative is involved here. F of x is equal to the square root of x. In order to take the derivative, we rewrite this in exponential form. F prime of x, you'd bring the 1/2 down, decrease the exponent by 1, and of course we can rewrite this then as 1 over 2 root x. This is my derivative. Now the mean value theorem says that it guarantees some point f prime of c such that f of b minus f of a over b minus a will be equal. Well, what we have so far then is we have f prime of c is equal to f of b. Now f of b, remember these are my points up here, a and b, so f of b will be the square root of 9 minus the square root of 4 all over 9 minus 4. So again we'll have f prime of c, square root of 9 is 3, square root of 4 is 2, 9 minus 4 is 5. So we get f prime of c equals 1/5. Now remember, from up above, f prime of x was 1 over 2 root x, so f prime of c is going to be 1 over 2 root c, and this is equal to 1/5. Now however you want to look at this, or solve this, if you want to cross multiply and divide if you can, but another way to think about this is the numerators are already equal, so I can just equate the denominators. If you cross multiply, you'll get the same equation. So what we end up here then is 2 root c equals 5. Root c dividing through by 2 is 5/2. And of course what we would do here then is to try and solve for c by squaring both sides. So we get c is equal to 5/2 quantity squared, which is 25/4. Now 25/4, if we look at this as an approximation, 6 times 4 is 24, and a remainder of 1/4, so 6.25. Now the question is 6.25 in this interval? And the answer is yes, it is. So this is the point C that is guaranteed by the mean value theorem in order to make this true. Now if we graph this in Maple, it kind of might give us a little bit more of an idea of what's going on. So jumping into Maple, I've already graphed this, square root of x. I just chose the scale that it automatically gave us. It almost is going to be a little bit difficult because it's almost a flat line between 4 and 9, but we'll do our best to have a look here. When we paste this, then we can kind of get an idea exactly what's going on in terms of my interval from 4 to 9. So we can see from here, when I plot this point and I plug in a 4, get this point out, square root of 4 is 2, so I get 2 over here. When I plug in a 9, I should get 3 back out. Square root of 9 is 3, and I can see over here I get that. And so what we're looking at here is this secant line between these 2 points. And like I said, this one's going to be a little bit difficult to see because it's almost a flat line here because of my scale. Well, what we have here then is the mean value theorem guaranteeing a point between, in this case, A and B. A is 4, B is 9. That guarantees that I'll have a slope of my tangent line. Well, if you look down here, I have 6 to 7. This would be 6.5. This would be 6 1/4. And so when I plug in, this is supposed to guarantee where I have that tangent line. And it does look like I do have a tangent line there that's parallel or close to parallel to that secant line. And actually, it does cross it. Let's go ahead and fix that up a little bit. So we want to make that parallel to that secant line. There, that looks better. So again, it's harder here for this particular graph because we have this graph is almost a flat line between here. If we could get some more curvature in that, it'll be a little bit easier to see. But we did find the point C that guarantees this. The next thing we want to look at is the increasing and decreasing behavior of functions. And again, the increasing and decreasing behavior can be talked about in terms of derivatives. So the first thing we talk about is we say, let's let f be a differentiable function on the open interval ab. Well, it makes sense if we want to talk about increasing and decreasing functions that it has to be differentiable. And we already talked about how if the first derivative is positive or greater than 0 for all values in a particular interval, then the function is increasing because the slopes of my tangent lines are positive. If the first derivative is negative or less than 0 for all points in the interval ab, then the function is decreasing on ab. Now, what this brings up is a conversation about a monotonic function. So let's go ahead and look at monotonic next. Of course, mono means one or singular. So monotonic functions or monotonic behavior means the entire graph of f of x is increasing on a particular interval, or the entire graph is decreasing on a particular interval. Now, if f of x is increasing, that would mean its first derivative is positive or greater than 0. If f of x is decreasing, that would mean that the first derivative is negative or less than 0. So let's look at the case where we're increasing. So let's look at increasing. So here we'd have an increasing graph. And if we look at this increasing graph, we of course read the graph from left to right, we can see that my slopes of my tangent lines here are always going to be positive. So I have an increasing function. Now for decreasing, I could have something like this, and when I have a decreasing function, the slopes of my tangent lines, you can see, are all negative. So that's what we mean by monotonic. It has this particular behavior. It's monotonic, it's constantly increasing on the entire graph, so it's monotonic increasing. This graph is decreasing, monotonic decreasing, because it's always decreasing. Now if we looked at another graph, this one is not monotonic, and it's not monotonic because here it's increasing, decreasing, and then increasing again. So this graph is not monotonic. However, I could say this graph is monotonic if I limited the values I'm looking at, let's say from the interval from a to b. Then I could say, oh, it is monotonic from a to b on these points. And it is monotonic from, let's say, a to b on these points. So we'll call this one a to b. It's monotonic increasing. From C to D, it's monotonic increasing as well. And B to C, of course, would be monotonic decreasing. So the entire graph taken as a whole is not monotonic, but I can define different parts of the graph where it would be monotonic increasing or monotonic decreasing. And sometimes that's what ends up happening, then that's what we want to do. Let's go ahead and look at another example. In this particular example, we're going to be finding intervals on which a function is monotonic. So if we want to find intervals on which the function is monotonic, we can kind of look up here and get an idea of what we need to do. The interval here, I'm monotonic increasing from a to b, and at b something interesting is happening. I have a slope of a tangent line here. So because I have a slope of my tangent line there, that's kind of giving me an idea of wherever I have a critical number where the slope of the tangent line is 0, I have the potential for my increasing, decreasing values to be changing. So apparently when slopes of tangent lines are 0, something important is going on, so we'll need to note that. First thing we want to do is take a derivative. The derivative of x squared plus 2x minus 4 is 2x plus 2. And then we set it equal to 0 in order to find critical numbers. Here we have 2x plus 2 equals 0. So we might want to look for the point where we have less than 0. So this would be where I have monotonic decreasing. And we'll change how we do this pretty soon. We'll put it in a slope chart, but this is how we find these points. Solving here, I'd have 2x is less than 2. Sorry, negative 2 when I subtract it across. Divide through by 2, and I'd say x is less than negative 1. So when x is less than negative 1, I have a monotonic decreasing function. So the interval where I have decreasing values is from negative infinity to negative 1. Of course, we never bracket infinity. Now doing the same problem, I would take f prime of x again, which was 2x plus 2 equals 0. And I'd say, okay, this time I want to know where this derivative is positive. So I'd make it greater than 0. And this is where I'd have a monotonic increasing. Solving, I'd have 2x is greater than negative 2. Divide through by 2, x greater than negative 1. So this is where I have monotonic increasing. So this is my interval where I'm increasing. So I'm increasing from -1 to positive infinity, and of course we never bracket infinity. So if we think about what this graph looks like, it appears that from negative infinity to -1, the graph is decreasing. From 1 to infinity, it's increasing. Now at the very point of 1, notice it's not bracketed. So what's going on here? Well, we already know what the graph of x squared plus 2x minus 4 is. This is a parabola that's opening up. So I'm not going to worry about the scale here. But apparently something important is going on here. Now to the left of this point, which I'm guessing is -1 from what we have here, I have negative sloping tangent lines. To the right I have positive sloping tangent lines. So from here I have a negative monotonic decreasing, and from over here I have positive values, so I'm monotonic increasing. So again, looking at these and finding these intervals is pretty straightforward as long as you can factor your derivative and get a nice solution there. Now another way that we can do this is by testing critical points or creating slope charts. Now this will be getting the same results as we did in the previous question. It's just a different way of doing it. So we had the function f of x is equal to x squared plus 2x minus 4. And we want to determine where it's increasing and decreasing. So I want increasing, decreasing intervals here. Well, instead of having two setups here where I test some less than 0 and some greater than 0, what I'm going to do here is a little bit different. I'm going to take the derivative and I'm going to set it equal to 0. And the reason we set it equal to 0 is in order to find critical numbers. Now critical numbers occur in two places. Critical numbers occur when the first derivative is equal to 0 or when it's undefined. But we don't have a denominator here, so I'm not worrying about that second case. When I solve here, I'd subtract the 2 across, divide through by 2, and I get x equal -1 is a critical number. Now what this critical number is then is a potential relative extrema. So this is a potential local or relative extrema. Well, we already have an idea of what this looks like. This is a parabola opening up. So if this is an extrema, which it looks like it is, it's probably going to be a relative min, because again, it's a parabola opening up. So what I do is I take this critical number and I plug it into a slope chart. Now what the slope chart is doing is it's checking to see what the slope of the graph is doing to either side of this critical point. So x equals -1 is my critical number. So this is just a number line from negative to positive infinity. Now I want to know what my slopes are doing to the right of -1. So what I would do is I would plug in some number over here into my first derivative. Because remember, my first derivative gives me my slopes and my tangent lines. So I could plug in any number I want. I could plug in 1,000,000, I could plug in 1,000,000,000, I could plug in 189. But the point is you plug in any number between -1 and positive infinity. And I plug in an easy number like 0. Now remember, we're plugging into the first derivative. So plugging into our first derivative, we have 2 times 0 plus 2. Now I don't care the magnitude of this number. All I care whether it is positive or negative. And we can see that this is going to be equal to 2, which is greater than 0, so I have positive values over here. And that's the important thing. I don't care that it's a 2, I care that it's positive. Now, to the left of -1, I want to test any number between -infinity and -1. And again, you can choose any number you want. It seems to make sense to choose, a reasonable number, a smaller number, so I'm going to choose -2. So we would plug -2 into my first derivative. 2 times -2 plus 2 is -4 plus 2 is -2, which is less than 0. It's negative. And again, I don't care about the fact that it's -2. The only thing I care about is the fact that it's negative. So this tells me that to the left of -1, I have a graph that's decreasing. To the right of -1, I have a graph that's increasing. So this might be what I have. Now I could be increasing like this, and so I have to be careful. I don't know about the concavity, and we haven't talked much about concavity yet. So this positive sloping tangent line could have a shape like this, or it could have a shape like this. My negative sloping tangent line could have negative sloping tangent line like this, or like this. So I'm not exactly sure what's going on here yet, but I have a pretty good idea that it's this case right here because I already have an idea of the general shape of my graph. Because I have this change between negative and positive, this point right here is a relative min. So because my slope chart tells me a lot of different things, let's go ahead and summarize what we have here. My slope chart says I have a relative min, at -1, and I'll find my y value here in a second. It says that my graph is increasing on the interval from -1 to positive infinity, and it's decreasing on the interval from negative infinity to -1. Now at -1, this is where my slope of my tangent line is 0, and so that kind of gave me an idea of where my critical number is occurring. Now if I want to find the y value that's associated with this x value of -1, I don't plug it into my derivative, I plug it into my original function. So if we plug in -1 in here, I'd have 1 minus 2 is -1, -1 minus 4 is -5. So from here I can even start to do a quick little curve sketch. So I'm going to be at the point -1, -5, let's say. Well, -1, -5. And it's going to open up, it's going to increase to the right, decreasing tangent line to the left. So I have decreasing tangent lines to the left, increasing tangent lines to the right. Now I don't know what these points are right now. I'm not saying they're hollow points, I'm just saying I don't know what these cross points are right now. Those are something that I'll figure out later as we kind of add to the different layers of this curve sketching technique. Let's go ahead and do the same thing again for a different function. Let's go ahead and find the critical points, find intervals where I'm increasing or decreasing, and any extrema that I can for the function f of x equal x cubed minus 12x plus 7. So the first thing to start would be to take a derivative, which would be 3x squared minus 12. I want to find critical numbers, and so I set this equal to 0. Now remember, critical numbers occur in two ways. Critical numbers occur when the first derivative is equal to 0 or when the first derivative is undefined. So solving here, I can factor out a 3, I'm left with x squared minus 4 equals 0. Dividing through by 3, I have x squared minus 4 equals 0 again. If you want to move the 4 across and take the square root of each side, or you can factor, difference of perfect squares, I get x equal plus or minus 2 for my critical numbers. So what I want to do is I want to take these critical numbers and plug them into a slope chart and figure out what's going on here. Now just because I have a critical number, it does not guarantee that I'll have extrema at these points. It could be a false positive. So let's go ahead and have a look at our slope chart. Now remember, your slope chart is just a number line. So it's a number line that goes from negative infinity to positive infinity, and I just mark particular values on here that happen to be critical numbers. Now this interval right here is 2 to positive infinity. This interval is -2 to positive 2. Endpoints are not inclusive. This interval goes from negative infinity to -2. Now I want to know on each of these intervals what my slopes of my tangent lines are doing. Are they positive or negative? Is my function increasing or decreasing? So what I do is I choose values on these intervals to plug into my first derivative to figure that out. And again, you can plug in any number. I'm just plugging in kind of some easier numbers. Now we don't care about the magnitude of these numbers we get back out, we only care about the sign of these numbers. So if we plug 3 in from right here into my original function, I could plug in, or sorry, into my first derivative, I could plug in here. Okay, but when I plug in here, it gets a little bit ugly. Here it would be a little bit easier. So if I plug a 3 in here, I get 3 squared is 9 minus 4 is 5. So I get positive times a positive, which is a positive value. So I get a positive number here. And again, I don't care about the magnitude, I just care about whether it's positive or negative. Plugging in 0 is pretty easy. 0 squared is 0 minus 4 is negative. Negative times this positive 3 would be a negative value. Let's go ahead and plug in a -3. -3 quantity squared is 9 minus 4 is a positive 5 times a positive 3 is a positive number. So this is what I have going on. I have my function is increasing, decreasing, and increasing again. And again, I could also be increasing in another way. I could be increasing as such. But I already know the general shape of a third degree polynomial. A third degree polynomial will go like this, or something like this if I have a positive leading coefficient, or something like this if I have a negative leading coefficient. So these are kind of my options, and I think that this one right here is kind of what we're working with. So it looks like here would be a relative max, and I'll figure out what that y value is here in a second. And here would be this relative min, and then I can start talking about intervals where I'm increasing and decreasing. So to summarize what's going on here, I have a relative max at -2, and we'll figure out the y value. I have a relative min at +2, and we'll figure out the y value. And then I have an interval where I'm increasing. In fact, I have two, so I better include the s there. -infinity to -2, and I'm also increasing from 2 to infinity. And I have a decreasing interval between -2 and +2. And notice nothing is bracketed here at all. Now, in order to get a little bit better idea of what's going on here, let's go ahead and plot this in Maple. Okay, in Maple, let's have a look. These are some older graphs. We have x cubed minus 12 times x plus 7. Okay, that's the function that we are expecting to see. So let's go ahead and plot that. And our y-axis scale here is pretty extreme, so we don't see a lot of what's going on. So I want to rescale this just a little bit. Hopefully this scale will work. Let's do vertical scale. Let's say -50 to +50. Let's see if, yep, now we get not a lot of nice curvature happening there. So let's go ahead and pop this into our journal doc. And see what we get here for a graph. Usually they come in huge. This one didn't come in so bad. And let's see if what we have here makes sense. Okay, it said that I have a relative max at -2. So here's -1, -2, so that makes sense. Oh, we forgot to find the y value. In order to find the y value here, I plug -2 back into my original function of x cubed minus 12x plus 7, and I get 23 back out. And again, this is plugging into f of -2 back to my original function. If I plug a +2 back in, I get a -9 back out. And again, this is found from plugging +2 back into my original function. So here's 2, and it does look like I have a relative min, a relative max. Now, it does look like that on this particular interval, from -infinity to -2, my function is increasing. From -2 to +2, it's decreasing. And from 2 to infinity, it's increasing. So this graph that we produced in Maple basically verifies everything that we have here. And I would really encourage you to do most of your graphs in Maple, because you can manipulate the scale pretty easy, and also you kind of get used to seeing what some of these functions look like. Now on a test or a quiz, you're going to have to be plotting these by hand, but the more you graph these in Maple, the more you get used to seeing some of these graphs and kind of an expectation for what they should look like. The last one that we're going to look at today is a trig function, so it will be very, very fun. We want to do everything else that we've already done. We want to find the critical numbers. We want to look for increasing and decreasing intervals for the function f of theta equals sine theta cosine theta on the intervals 0 to 2 pi. Now for a trig function, it's usually very important to have an interval, because the trig function repeats itself over and over again. It has that periodic nature across the entire real number line. So that's why we usually limit this between 0 and 2 pi or 0 to pi, etc. Well, the first thing we need to do here is to find critical numbers. So let's go ahead and look at finding critical numbers first. Now when we talk about critical numbers, we know that this involves a derivative somehow. So let's go ahead and look at a derivative. This is a function times a function, so I'll need the product rule here. So I'll have the first function times the derivative of the second plus the second function times the derivative of the first. So we haven't actually taken the function derivative yet, but we've set it up. So dragging the sign along, always put parentheses around the arguments of your trig function. The derivative of cosine theta is a negative sine theta times the derivative of theta, which is 1. So I am using the chain rule here, but because my argument is just theta, it's not very exciting. I just get that multiplication times 1. The derivative of the sine theta here is the cosine of theta times the derivative of theta, which is 1. So rewriting, I have cosine squared theta minus sine squared theta. Now, critical numbers occur wherever the first derivative is equal to 0 or undefined. I still don't have a denominator here, so I don't need to worry about it, but I'm going to take the numerator and set it equal to 0, because this is how I will find my critical numbers. Now, there's quite a few different ways that you can look at this. Cosine squared minus sine squared is actually a nice little trig identity. I believe it's equal to the cosine of 2 theta, but that really wouldn't help us out too much here. So I'd like to look at this in terms of solving and trying to figure out a function that I can solve for theta here. So solving algebraically, I could move the sine squared across, and I would get sine squared of theta equals cosine squared of theta. So whether you move the sine across, you move the negative cosine over and divide through by negative, you get sine squared equals cosine squared. And then what we can do is divide through by cosine squared theta, and we get sine squared divided by cosine squared is tangent squared theta equals cosine squared divided by cosine squared is 1. Taking the square root of each side, I get the tangent of theta equals plus or minus 1. And because you know your unit circles so well, you know that multiples of pi over 4 will have a tangent of either positive 1 or negative 1 depending on which quadrant they're in. So the critical numbers here, we're going to have quite a few of them, will be 1 from each quadrant. We'll have theta equals pi over 4 as a critical number because the tangent of pi over 4 is a positive 1. We'll have one at 3 pi over 4 because the tangent of 3 pi over 4 is a negative 1. We'll have one at 5 pi over 4 because the tangent of 5 pi over 4 is a positive 1. And we'll have 7 pi over 4 because the tangent of 7 pi over 4 is a negative 1. Now this would go on forever in either direction, except remember I do have this limitation of being between 0 and 2 pi. So what we want to do is take all these numbers and put them into a slope chart. However, this slope chart will be a little bit different because all the other slope charts I worked with before went from positive to negative infinity. This one only goes from 0 to 2 pi. So let's go ahead and look at a slope chart. And we're going to need plenty of room for this one because we have so many critical numbers. So this slope chart goes from 0 to 2 pi. It doesn't go from negative to positive infinity. Okay, so let's go ahead and split this up into quadrants. This would be pi, this would be 3 pi over 2, this would be pi over 2. And so here I'd have 0 to pi over 2 would be a pi over 4. So theta equals pi over 4. Theta equal 3 pi over 4. Theta equal 5 pi over 4. And theta equals 7 pi over 4. So the intervals I'm interested in are these larger marks right here. The smaller tick marks are just kind of points to help me keep track of what's going on here. But the interval here would be 0 to pi over 4. This interval would be pi over 4 to 3 pi over 4. This tick mark just kind of helped me scale things. So again, I want to take the first derivative and evaluate it at some point in each of these intervals. And again, I can choose easy values or I can choose complicated values. Okay, well, let's go ahead and jump up here and have a look at our first derivative. Our first derivative was cosine squared minus sine squared. So let's go ahead and keep that in mind. My first derivative was cosine squared minus sine squared. So 0 to pi over 4, I think our only standard angle we could plug in is pi over 6. So when we plug in pi over 6, we want to figure out what's going on here. We'd say, okay, we can scoot down here, and we'd say the cosine of pi over 6 quantity squared minus the sine of pi over 6 quantity squared. So this is f prime at pi over 6. Well, the cosine of pi over 6 is square root of 3 over 2 quantity squared. Sine of pi over 6 is 1/2 quantity squared. So it looks like I have root 3 quantity squared would be 3/4 minus 1/4 is 2/4. Again, the only thing I really care about is that this is positive on this interval, so I know I'm increasing. Now, because this is a trig function and I have this periodic nature, I'm going to start seeing a pattern here, but I do really need to check everything in this interval. Now, from pi over 4 to 3 pi over 4, an obvious choice would be pi over 2. Cosine of pi over 2 is 0. 0 squared is 0. The sine of pi over 2 is 1 squared is 1. 0 minus 1 is negative. Now between 3 pi over 4 and 5 pi over 4, an obvious choice would be to check pi. So the cosine of pi is negative 1 squared. Negative 1 squared is positive 1. The sine of pi is 0 squared is 0. So I have 1 minus 0, which is positive. And now you start to see kind of our pattern, positive, negative, positive. But not all graphs will follow this entire pattern, so you have to be really careful about that. Between 5 pi over 4 and 7 pi over 4, I think 3 pi over 2 would be an easy one to plug in. The cosine of 3 pi over 2 is 0. 0 squared is 0. The sine of 3 pi over 2 is negative 1. Negative 1 quantity squared is 1. 0 minus 1 is minus 1. And again, the only thing I care about here is that this is negative. Now between 7 pi over 4 and 2 pi, I'm not going to have a real nice angle to choose here other than maybe something like 11 pi over 6. Now if you plug in 11 pi over 6, basically you're going to have the same thing that we did down here, except when I plug in the sine of 11 pi over 6, I'll have a negative value here. But when you square a negative value, it doesn't end up mattering. So let's just go ahead and check 11 pi over 6 here. The cosine of 11 pi over 6 is a 3 over 2, quantity squared. The sine of 11 pi over 6 is a negative 1/2, but that doesn't change anything here because it's being squared, so I know that this is positive. So my function is going to go positive. Sorry, it went negative. It's going to go positive, negative, positive, negative, positive. So it looks like right here I have a relative max over here, and here I'll have a relative min, and here I'll have a relative min. Now right here at this point I have neither a max nor a min because I don't have anything decreasing on the other side. Those are just where my graph ends. So what we can do now is go ahead and take a look at this particular function in Maple and see if we can match up what Maple says with what we have. So I want to take the graph of sine of x times the cosine of x. Use a lowercase x though. Let's see here. Here we go. And of course, to figure out what this plot looks like, look at a 2D plot. And this is nice because it scaled our horizontal axis in terms of pi. Now we were looking 0 to 2 pi, so let's go ahead and change our scale. Right now the horizontal scale goes from negative 2 pi, so let's change this to 0 and apply. And for vertical, I'm just going to go a little bit higher because I think that this graph goes up to 1/2 and we want to see that maximum point, so I'm going to change this just a little bit. Okay, now we can see that it does indeed go up to positive 0.5, negative 0.5 for our max and my min. So let's go ahead and grab these points and see if they match up with what we did in Journal. So what Journal said was, what the work that we did in Journal said is we have a relative max at pi over 4. Well, here's pi over 4, there's my relative max. So this is the point, pi over 4, and it looks like 1/2. And I could have figured this out by plugging pi over 4 into my original function. I have another relative max here at 5 pi over 4, 1/2. And Journal Doc says relative min at 3 pi over 4. Whoops. At 3 pi over 4, negative 1/2. And over here at 7 pi over 4, negative 1/2. Okay, so everything we did in Journal seems to add up to everything that we did in Maple. Now, relative extrema. Let's go ahead and look at our relative mins first. I have a relative min at 3 pi over 4, negative 1/2. I have another relative min at 7 pi over 4, negative 1/2. I have a relative max at pi over 4, 1/2. And I have another relative max at 5 pi over 4, 1/2. Now notice these endpoints right here at 0 and 2 pi, they're not extrema at all. Okay, there's not a max or a min there, they're just endpoints. Now I also have intervals on where my function is increasing, so I have increasing intervals. Now these increasing intervals would be from 0 to pi over 4, 3 pi over 4 to 5 pi over 4, and 7 pi over 4 to 2 pi. So again, 0 to pi over 4 is increasing. 3 pi over 4 to 5 pi over 4 increasing, and 7 pi over 4 to 2 pi increasing. And actually, we were looking at endpoints that were bracketed, so I guess we could bracket the 0 and the 2 pi because they were given to us as bracketed. Now these are ordered pairs. These are x, y values. These interval notations are x to some x value. Okay, so these are not ordered pairs. Now intervals where my function is decreasing, I list my x values. From pi over 4 to 3 pi over 4 I'm decreasing, and from 5 pi over 4 to 7 pi over 4 I'm decreasing. So again, from pi over 4 to 3 pi over 4 I'm decreasing, and I'm decreasing again from 5 pi over 4 to 7 pi over 4. So this is my decreasing intervals. And again, these are not ordered pairs, these are interval points across these values. Now, we've looked at quite a bit of stuff today in terms of slope charts, and we're going to be using slope charts a lot, so it's kind of a good thing to get good at. Pretty soon we're going to be adding a second derivative test where we're actually looking at the concavity. Now, concavity has to do, if we're talking about, second derivative here, the rate of change of our first derivative, so our rate of change of our increasing or decreasing function. So in terms of concavity, this would have negative concavity here. This would be a positive concavity. This would have negative concavity, and here we'd have positive concavity again. But that's when we're checking our second derivative tests. And you can get a good sense of what concavity means by this graph. A lot of people look at concavity as thinking, will it hold water or not? This one definitely won't, so negative. This one would, positive, negative, and positive concavity. Some concavity wouldn't hold water even if it was positive concavity, but it gives us a good sense for what concavity means. But that will be coming up in one of the next lectures. Thank you.